try this again. Okay, so when we're changing dimensions, not only can it affect the perimeter and the area of two-dimensional figures, but changing dimensions also affects the volume of a three-dimensional. So let's just have a little review here. This is from yesterday. When changing dimensions, it can be referred to as a scale factor, or how does the book like to call it? Ratio of corresponding sides. Yeah, ratio of corresponding sides. So they mean the same thing, don't they? Another thing in here, I use the word dimensions, so see, sometimes they might call it ratio of corresponding dimensions, okay? So we got to know that if we set up a ratio of dimensions that correspond between two figures, when we set that ratio up and simplify it, we will have our scale factor. That should tell us what the scale factor is. Okay, let's be reminded, if the figure gets larger, whether it's two-dimensional or three-dimensional, the scale factor or ratio of corresponding dimensions must be what? Greater than 1. Yeah, greater than 1. So if the figure, be it two-dimensional or three-dimensional, if it gets larger, then your scale factor better have been more than 1 or better turn out to be more than 1, greater than 1. Well, if it gets smaller, then what should we count on? The scale factor should be what? Less than 1, yeah, less than. So if our new figure, be it two-dimensional or three-dimensional, if it gets smaller, well, your scale factor better be less than 1, or better turn out to be less than 1 if you're the one looking for it. So when we're asked for the ratio of volumes, our next arrow here, when we're asked for that, they're really actually asking us how many times larger or smaller the figure gets. So just like yesterday, so if they ask you for the ratio of volumes, you can think of it like this. How many times larger is the new figure? Or how many times smaller is the new figure? Okay? So let's go practice here with some couple of prisms. Every dimension of rectangular, let's put an arrow there. Every dimension of rectangular prism A is doubled to form rectangular prism B. How many dimensions does this prism have? How many dimensions does a prism have?
4, 6, 8, 12.
3. It's a three-dimensional figure. It has 3 dimensions. It's got a length, a width, and a height. So the length of the base, the width of the base, which is a rectangle, and then the height, because it's three-dimensional. It's not just a two-dimensional base. Okay, so what are the dimensions of prism B then? What are they going to be? Well, let's do it on the figure first. What's 5 doubled? 10. So that's going to be 10 inches on prism B. How about whether we call it length and width, doesn't matter which one we call it. 6 inches is going to become 12 inches. And the height of our prism is going to go from 3 to 6. Okay. So what are the dimensions of prism B? They are 10 by 12 by 6. 10 by 12 by 6. Okay. So what is the ratio of the corresponding dimensions? Okay, so what is the ratio of corresponding dimensions? I think we have 3 different ratios we can actually set up here. So give me one. What's a ratio we could set up of corresponding dimensions? Remember, what goes upstairs, the original or the new? No, the new. Okay, so Samuel, what's one of the ratios we could set up?
10/5.
10/5. Or, what's another one we could set up? Blake?
6/3.
6/3. Ratio of corresponding dimensions. Or, what's another one we can set up? Sydney?
12/6.
12/6. no matter what we do, all of them come out to what? 10 over 5 is the same as 2 over 1. 2 over 1 is the same as 2. 6 over 3 is the same as 2.
1/2.
Only if it's 3 over 6. 6 over 3 is 2. 12 over 6 is 2. Our 2 over 1, which then basically we're going to simplify. Remember, we always want our scale factors simplified. Okay? So we got the scale factor, didn't we? We doubled the dimensions. And when we set up our ratio of corresponding dimensions to corresponding sides, we got our scale factor, just like we said. They mean the same thing. Okay, so what is the volume of prism A? Does anybody know how to find the volume of a rectangular prism? Length times width times height. So we're going to do 5 times 6 times 3. Figure that out. What is that? 5 times 6. And then multiply that by 3.
180.
That's not 90. Amazing, it's 90. Okay. Anybody know what the label would be on that? Inches cubed. When you take inches times inches, they become inches squared. And then you take them times inches again, because we did 3 dimensions. We end up with inches cubed. So it has a volume of 90 inches cubed, or cubic inches. We could write it out in words. Volume of prism B. What are we going to do to get that one?
Is that a little 3 or 2?
It's a little 3.
10 times 12 times 6.
10 times 12 times 6.
It's 2.
That one's 220? No, it's a lot more than that. Well, 10 times 12 is
120.
120. So we need to multiply that times 6. 720. And what would its label be? Inches cubed. Okay. Boy, did it get a lot bigger, huh? Went from 90 inches cubed to 720 inches cubed. Do you know what a cubic inch means? What's that mean? What's an inches cubed? What are they talking about? Well, what is it? Tell me what it would look like. What would it look like? In real life, what would a cubic inch look like? Any idea? What a cubic inch would look like? Well, the first word gives it away. Cubic. It's going to be a what? A cube. And it's a cube that is got dimensions of what? 1 inch by 1 inch by 1 inch. So imagine an inch, okay? So you have this cube so you have a block. You have a cube that is 1 inch wide by 1 inch deep long by 1 inch high. So this one is saying that first prism would have 90 of those that would fit inside of it. And the other one would hold 720 of them. Okay, so now we're going to find the ratio of the volumes. What goes upstairs first in a ratio, the original or the new? Always the new. So 720 over 90. And we will simplify that also. Well, first of all, you can cross out the zeros, right? And then you can just say to yourself, what's 72 divided by 9? 8, yeah. So the ratio of the volumes is 8. So remember the ratio of the volumes, it says it up here. I'm going to go back up here. It says right here. When asked, let's underline this. When asked for the ratio of volumes, and that's what we just found. We just found the ratio of volumes. When asked for the ratio of volumes, they're really asking how many times larger or smaller the figure gets. Huh. So our prism got how many times larger? Didn't it get larger? How many times larger did it get?
8 times.
8 times larger. You got 8 times larger. So how is the ratio of the volumes related to the ratio of the corresponding dimensions? We're going to say, oh, I don't know why. I should probably get that changed up. I don't really like the way they say that. So 8, remember when we have the ratio of corresponding dimensions, that's the same as the what? What do we call that? What do we call this? Scale factor. Let's put that. Let's write that underneath that. We're really talking about the scale factor. So the ratio of volumes, how is it related to the scale factor? Well, what do you think we could do with that scale factor of 2 that would get us to 8? What do you think we could do with that scale factor of 2 to get us to 8?
2 times 4.
2 times 4. But remember yesterday when we were doing area, we took the scale factor times itself.
2 times 2 times 2.
2 times 2 times 2, yeah. So let's do that. Let's say that this, there's 3. It's 3-dimensional, remember? So 2 times 2 times 2 gets you that 8, that ratio of volumes. So we're going to say that the ratio of volumes, we didn't do the experiment for this one, to actually see it happen. Ratio of volumes is the scale factor cubed, or in other words, multiplied by itself 3 times. So 2 was our scale factor. 2 cubed, 2 times 2 times 2 got us our ratio of volumes of 8. So the next question I ask you is, do you think we could have found the ratio of volumes now that we know that without finding the volumes of each of them? Yeah, what could we have done? The question up there, number 7, it says, do you think we could have found the ratio of volumes without finding the volumes of each? Because sometimes, what if they are talking about something that you don't know how to find the volume of? Are you going to have to figure out how to find the volume of that before you're going to be able to find the ratio of volumes? If you know the scale factor, what can you do? What do you think you can do? If you know the scale factor, what did we just write down? Okay, we're going to say yes to this. We could have found it without finding the volume of each. I don't want you to be coming back tomorrow and saying, I could not do this problem because I don't know how to find the volume of a sphere. I'm going to be like, you didn't need to know how to find the volume of a sphere. All you have to do is, if you know the scale factor, so yes, we can take the scale factor and cube it, like we just set up above. So the question was, do you think we could have found it without? No, we didn't need to know those volumes. We found the volumes and we verified that it works, but we don't really have to have it. And that's what you're going to find in your homework for tomorrow, is, you know what, there are going to be times you're going to be like, I don't know how to find the volume of that. You don't have to know how. Okay? Anybody have any questions? Okay, let's go to the back side and practice some problems where we maybe can do some stuff without having to know volume formulas. So we have a cube that has a side length of 4 inches. Okay? So anybody know how to draw a cube? Okay, go for it. Go ahead and do it on your paper. Draw yourself a cube. And it has dimensions of 4 inches, so a 4 by 4 by 4. Just kind of nice to have a visual while we're talking here. So a cube has a side length of 4 inches, and all we have to do is say the side length, because in a cube, all a width and a height are all the same. So we can say that it's a 4 by 4 by 4. A scale factor of 2 is applied to the cube to form a new cube. A scale factor of 2. Would you circle that? That's important. Because now we're going to have a new cube. Is our new cube going to be larger or smaller? Better be larger, right? Okay. So if you just want to, draw a larger cube, just, keep practicing your drawing skills here. And then what would its dimensions be? What's the dimensions of that? 8 by 8 by 8. We're doubling. Our scale factor is 2. So we have an 8 by 8 by 8. Now it says how many of the original cubes would fit inside the new cubes? 2. New cube. Just 2? 4? 8? Okay. So why 8, Seth?
Because
So it can fit twice as much. Well, then wouldn't only 2 of them fit in there? Got to get these out this morning, but I think I just happen to have something that might give us a visual of it. And let's see. So here is one that has, okay, can we go with this one right here? Here's one that's a 2 by 2 by 2, okay? And this one is a what? What's this one? A 1 by 1 by 1. So if we double the 1 by 1 by 1, do we have a 2 by 2 by 2? 1 doubled is 2, right? Okay. So in what I'm hearing, some of you are thinking then two of these should fit inside here. Others of you say 4 of these should fit inside here. And then Seth says, no, there's 8 of them. Oh, now you want to back up to 4? Okay. Got some girls right up front here who are going to check this out for you. Okay, but here, how many are in there right now? 4. Is it full?
16.
Look at there, 7. How many would it hold? It would hold 8. Yeah. Because I got 4 of them in there just on the bottom layer, don't I? So I could actually put 8 all together in here, couldn't I? Yeah, so could you pass this back, let me see it after you're done, and Adam see it after that? So basically then, we double the dimensions of this one, so how many of the original are going to fit inside the new one? How many do you think? What are we going to go with? 8 of them, yeah, we're going to go with 8 of them are going to fit inside of there because we just actually saw it, and here's all we have to really do, okay? We don't even have to find the volume of these guys because the ratio of the volumes, remember, tells us how many times larger or smaller it will get. So what we can just say is that we're going to have 2 times 2 times 2. This would be our ratio of volumes. Let's write that. Let's write the ratio of the volumes without having to find the volumes. Without having to find the volumes, we know that we can take the scale factor and cube it. Take it times itself 3 times, and we get 8. So our answer to this one is going to be 8 of the original cubes. And I do want you to write some sentences that will help us see what the real answer is in your homework here. So let's do it in our notes too. 8 of the original cubes fit inside the new cube. Because that was the question. How many of the original cubes fit inside the new cube? We discovered 8 of them should. Okay. Ready to move on? We have a cylinder. Give me an example of a cylinder in real life.
We write it in soup
A soup can. You could draw a cylinder if you want. Soup can, a what? Pop can. So you have a pretty good idea of what a cylinder looks like. We have a cylinder that has a radius of 8 centimeters and a height of 14 centimeters. So a radius is halfway from the center of the circle. So there's circles at the top and bottom of the cylinder. So 8 centimeters. A radius is from the center to the side. And a height of 14 centimeters. Each dimension of the cylinder is multiplied by 1/2. Okay? Would you underline that right there? Multiplied by 1/2. What does that tell us? Multiplied by 1/2. What's it really saying to us? Multiplied by 1/2. What's it really saying to us? Because you know what? I don't want to draw a cylinder. I'm not in the mood right now. I just
So, like, the top of it, it has 8, and that's like 1/2 of it.
So the new one's going to be, then what's the new one's radius going to
It's
be?
gonna be 16 on top.
Is 16, the new one is 16 half of 8?
Wait, no, 4.
It should go to 4, shouldn't it? So when they say multiplied by 1/2, aren't they giving us the scale factor, you guys? That's what I want to hear from you. When they tell us what to multiply by, they're saying the scale factor is that multiplier. So when Adam just said the new one's going to have this, you know, it's going to go to 16, because our scale factor is less than 1. So is this cylinder going to be larger or smaller? It better get smaller, right? Yeah, it better get smaller. Okay, so how would the ratio of volumes compare to the ratio of corresponding dimensions?
You get smaller.
So they're asking us for the ratio of volumes is really what they're doing here. What do we do to get the ratio of volumes?
Times 1/2, 3 times.
3 times, you're right. 1/2 times 1/2 times 1/2. When you multiply fractions, you multiply across the top. What do we have upstairs in all of them? 1. So 1 times 1 times 1 is 1. So equals 1. And 2 times 2 times 2 is 8. So 1/8 is the ratio of the volumes. And we got it by doing what? What did we do?
Times in it by
We cubed the scale factor. Yeah, we cubed the scale factor. Okay. So remember while we're gonna talk about this, we're gonna say the new cylinder. How does it compare? The new cylinder is 1/8 the size of the original. The new cylinder is 1/8 the size of the original cylinder. Did you write that, Preston?
Yeah.
You got it? Okay. I think we got one more to practice together. I think this time they're going to make us find the scale factor. So let's circle that right here. This is what they're asking us to do. What is the scale factor? Oh, okay, we got to find it this time. So we have a cone that has a volume of 36 pi centimeters cubed. And that's kind of important. Volume of, let's underline that. And every dimension is multiplied by a scale factor to form a new cone. Notice they didn't tell us what the scale factor was. The new cone has a volume of 972 pi centimeters cubed. Okay, so let's set up a ratio of volumes. Because we got them this time, we don't even have to find them. They're giving them to us, so let's use them. What's going to go upstairs, the new or the original? The new. So downstairs, we're gonna put 36 pi. The pi is not part of the label, it's part of the volume. Then when they leave the pi symbol in there, they're just telling us this is the exact volume. They didn't do any rounding. What is the rounding for pi? 3.14, yeah. But they didn't want to round, so they just left it in there. Okay, but if there's a pi upstairs and there's a pi downstairs, what can we do with them? Get rid of them. We can cancel them. We can go like that. We don't have to worry about that pi being in there. And now, we're going to simplify 972 over 36. I'm thinking a calculator would be nice for this. How about we just try and see if 36 goes into 972? 972 divided by 36. What is that? 27, okay? Now, do we feel good about that? Because, remember, is the new one bigger or smaller? Bigger, okay. So this 27 is kind of a big number. I'm feeling kind of good about that. But is that what they wanted? Did they want the ratio of volumes? No, they want that scale factors. How are we going to get that?
27 times, like, would you divide 27 3 times?
Well, you can't really divide by 3 because what is 27 divided by 3?
No.
I think I know what you're trying to say though. Do we have to find whatever multiplies times itself 3 times gives us 27?
Wait, so it'd be 9.
9 times 9 times 9? No. 3 times 3 times 3?
Yeah.
3 times 3 is 9, and 9 times 3 is 27. So remember, ratio of volumes is the cube of the scale factor. Okay, ratio of volumes is the cube of the scale factor. So we needed to find out what times itself 3 times gives us that ratio of volumes. So we're going to say the scale factor is 3. The new cone is 27 times bigger, but that does not mean the scale factor was 27. The new cone is 27 times bigger. That's a lot. But yet all they did was triple the dimensions. That's what we found out. If you triple the dimensions of a cone, the new one is going to be 27 times bigger. Okay? So any questions on any of it that we went through? No? Okay. Then